So for unit 3, this is quite relatable to what you have learned in chapter 2 or unit 2, which is volumetric analysis. So the redox titration is one of the example of volumetric analysis as well. So it still use the concept of titration, but the chemical reaction involved will be on the reactions of redox. Okay, so redox basically is the chemical reaction involving reduction and oxidation at the same time. Okay, they occurred simultaneously. So what we will cover in this unit, we will look into the concept of redox reactions, which is on the reducing agent, oxidizing agent, so on. So oxidant, reductants, and some of the examples and types of indicators commonly used in redox titration. Then we will see the equivalent point. So the equivalent point for redox titration is slightly different than in acid-base titration. So in acid-base titration, you are trying to reach maybe the point of neutralization, but here it is based on, we will see they are determined by the number of electrons, okay, where the differences of electrons. Then standards, and then only we will go into this several type of redox titration. First, we're going to look into the permanganometry. Okay, so it involves potassium permanganate or permanganate ion. And then we will look into chromatry or dichromatry. So this one involves dichromate ion. And then the iodo and iodimetry. Okay, there's slight different. The spelling is just different on iodo and iod, but the method itself, there is quite significant difference on how they are being used, okay, in the lab. And then the last one we will look into is serimetry. This one is involving cerium ion, okay. And lastly, on the some of the example for pharmaceutical analysis application. So introduction, we will look into what is redox. I think this one is already covered in stoichiometry back in your first semester in your general chemistry. So redox basically is the acronym of reduction oxidation. So the chemical reaction have a reaction and also oxidation reaction happening at the same time. So one substance will be oxidized while the other will be reduced. So the oxidized substance will donate electrons while the reduced substance are going to receive those electrons. So a reducing agent will undergo oxidation. Okay, it is like the opposite, reducing agent undergo oxidation. So this is called reductant. And oxidizing agent, which is oxidant, will undergo reduction. Okay, will undergo reduction. So these are some examples of the redox reaction. So if you look on the first example over here, you have copper 2 plus ion plus magnesium metal. So this is neutral. It reacts somehow and then producing magnesium 2 plus ion and also copper, okay, copper metal without any charge. So from here, you can see that the copper 2 plus has an original of the oxidation number is from 2 becoming 0. So this one, when it is in neutral state, it is considered to be 0. So copper 2 plus undergo reduction, while for magnesium, from oxidation number 0 become 2 plus. So this one is considered to be oxidized. So copper 2 plus receive electron, okay, to form this copper metal, while the magnesium 2 plus release or donates electron to form magnesium 2 plus. So it must remove 2 electron so that it become 2 plus. So in oxidation, there are several criteria in which you can look, okay, for oxidation and reduction in order to identify them. One is by the gaining of oxygen for oxidation, and then loss of hydrogen and loss of electrons, like this, for example, the magnesium lost electron. So it is undergoing oxidation reaction, and then it increase in the oxidation number, which is true as well for this magnesium, from 0 to 2 plus. Okay, so it fulfills category 3 and 4. This, but it does not contain any oxygen or hydrogen, so you cannot identify it by referring to number 1 and number 2. While for reduction, it will either lose oxygen, gain hydrogen, gain number of electrons, and also decrease in oxidation number, which is true in this copper. So it increase electron, so it gain electron. So copper 2 plus 2 electron, forming this copper metal. Okay, and also decrease in terms of the oxidation number, which is from 2 plus, from 2 becoming 0. Okay, from 2 to 0. So it decrease in the oxidation number. Then if you look over here, so this is involving non-metal. Okay, involving non-metal between chlorine gas and also hydrogen gas, forming this hydrochloric acid. So if you look on the reactant side, you have chlorine gas, Cl2, and also H2. So originally both are having oxidation number 0, 0. Okay, 0, and this one is 0. But when it become HCl, the H plus is plus 1. Okay, H plus, when it dissociate, become plus 1, while the chlorine become negative 1. So that means the chlorine is having decrease in oxidation number from 0 to negative 1, while hydrogen increase from 0 to positive 1. Okay. And then you have other example. This one, ethane burns in oxygen to give out carbon dioxide and also water. So you can refer to the oxidation number for carbon, originally from negative 3 over here to become positive 4. So that is oxidation, while oxygen from 0 to negative 2. So that is the reduction. And this one, iron, okay, iron metal 0 to iron 3 plus. This is iron 3 plus oxidation, while the oxygen is still undergoing reduction reaction. Okay, and I place also this example reaction involving magnesium and also zinc chloride. So forming magnesium chloride plus zinc, okay, plus zinc. So the magnesium originally has 0 oxidation number. It become positive 2. So that means it is undergoing oxidation reaction, while the zinc is from positive 2 to 0. So it undergoing reduction reaction. Okay. So no changes in the number of oxygen and hydrogen in this reaction. So mainly you have to identify the oxidation and reduction reaction based on the oxidation number and also the electron, from number of electron. But from this type of reaction, it is easier just to determine using the oxidation number, because if you want to know on the what do you call that, based on the electron, then you have to go to the half equation like this. From the half equation, you will be able to identify easier in terms of whether it gains or lost some electron. But if it is written in this full equation like this, okay, for example like this, then I believe it is easier to detect which one is undergoing oxidation or reduction based on their oxidation number. we can still extract from this information in order to write the what do you call half equation. Okay, you can go from Mg, okay, Mg, and then an arrow forming Mg2 plus 2 electron. So that means it donates electron. Okay, while zinc 2 plus 2 electron, okay, gaining 2 electron from the magnesium to form this zinc ion, like this. So this would be the half equation. Another example involving iron oxide, okay, iron trioxide, and also carbon, okay, carbon atom. So the iron originally from having oxidation number 3, okay, to 0. So that means it is being reduced, okay, from positive 3 to 0 is being reduced, while the oxygen, if you check, it still remain negative 2 over here, and on this side also negative 2. But for the carbon, from 0, it become positive 4. So carbon is undergoing oxidation, while the iron is undergoing reduction reaction, but the oxygen remain the same. So this would be the half equation. Okay, another example of half equation. This one involving manganate. Okay, manganate ion. So from here, like this, it is not written what is the oxidation number for Mn. So you have to calculate first. So this means that the calculation should be, if you want to find out the oxidation number of Mn, this is more like algebra, okay, in which that you consider this to be an x value, okay, plus, so for oxygen, it should be negative 2. So 4 times negative 2 should be negative 8. So x plus negative 8 equal to, this is considered to be negative 1. When there is just a negative sign, so the number or the value is negative 1. So the whole oxidation number for MnO4 is negative 1. But what you want to know is the oxidation number for the manganese alone, this one. So when you calculate, you are going to find out that the oxidation number for manganese is positive 7. Okay, positive 7. So from positive 7, it goes to positive 2. So there is a difference in terms of 5 electrons. So that means the manganese is undergoing reduction reaction. Okay, another way you want to know the oxidation number is whether you calculate correct or not. You just add here, okay, Mn2 plus, so this is 2. You have to add with the number of electrons. So if you get 5, 2 plus 5, you get 7. So if the answer is the same as the oxidation number that you calculate over here, then that is correct. But if you got different number, then your calculation might be incorrect. So you have to recheck back again. And then the half equation for the second part, the half equation 2 involve ion Fe2 plus. So here the oxidation number starts from positive 2 become positive 3. Okay, so an increase of 1. So that means it undergoes oxidation reaction. So this one reduction, this one oxidation. So the full equation, you just combine these two together, but you have to be careful to make sure that the number of electron is the same. If here is 5, then you have to times this, all of this with 5 as well. So that means 5 Fe2 plus, 5 Fe3 plus 5 iron, because here the iron is being donated. Okay, and over here there is 5, this 5 electron will be accepted by this ion. So 5 donated, 5 accepted. So that's why over here you must times it with 5. Then only you will have a balanced equation, so that you can cancel out. Okay, you can cancel out the electron. because the electron, one is on this side and one on the right side, so you can cancel out because this has become 5. Okay, but the rest you just write lah. Okay, the rest will be written MnO4, 8H plus, and then 5 iron 2 plus. Okay, then arrow Mn2 plus, plus 4 water, and also 5 iron 3 plus. So that is how you write the full equation. Okay, full equation by combining the two half equation. So some common example of the oxidizing agent, you have potassium permanganate. Okay, this is the number of oxidizing, the oxidation number for the manganese itself, and then potassium dichromate for the chromate, which is 6. This one is 7, and over here we have this EO. This is what we call as the redox potential. The ability of this species or this chemical to give out electron, okay, to donate electrons for the redox reaction. Okay, higher value means it is more readily available to donate those electrons. So this one, potassium dichromate, and then free chlorine, just chlorine itself, and then iodine. You can also use ammonium cerium sulfate or potassium iodide. So higher value of this redox potential, that means it is a better or stronger oxidizing agent. Then for reducing agent, example is ammonium iron sulfate, oxalic acid, titanium chloride, and sodium thiosulfate, arsenious oxide. These are some of the common reducing agent that is mostly used in redox titration. And then in terms of standard, okay, as usual, when you are doing a titration, of course, you have the analyte, which is in the conical flask itself, and also the titrant, or the solution that is in the burette. So the one that is in the burette is normally what you prepare, okay, which contains standard solution, meaning that you know the exact concentration for that particular solution. Otherwise, if both is unknown, then you cannot calculate lah. Okay, you cannot analyze the concentration of the analyte. So these standard solutions are made by dissolving an exact weight of a substance. Okay, but that substance must have very high purity. Okay, it needs to be stable and best to be anhydrous without any water or solvated water. Okay. So if requirement is not met, okay, all of these requirement, if it's not met, then it will be considered to be as the secondary standard, which is this one. So primary example like sodium carbonate, okay, potassium chromate, oxalic acid, or potassium hydrogen iodide. And secondary standard are normally prepared, okay, by referencing it to our primary standard. Okay, you have to react it with the primary, okay, in order to set that secondary standards. And then the type of redox indicators. So there are 3 which is available. One is called as self-indicators. So this one, the reaction itself will show the maybe color changes, okay, without any addition of indicators. Like for example, back in acid-base titration, you probably add phenolphthalein because both of the acid and base are colorless. Basically, the color like water. So if you mix solution, both are having the same type of color, so you are not going to see any difference at all. But for self-indicators, in terms of redox reaction, one of the what do you call that species could be the analyte. The analyte probably is colorless, but then you are going to add, for example, like in potassium permanganate titration, the permanganate is very dark purple. So when you add into the analyte, which is clear, it will change to the purple color as well. But the point for you when you want to stop is when it turns very light pink. So that is considered to be self-indicators, okay, which is acidified potassium permanganate. And then external indicator. So this is kept separately. So solution being titrated will be removed every few minutes and then tested with the external indicators. That means you have to remove some of the solution from the analyte, okay, from the conical blast, take some and then test with the external indicator. Is it already reach equivalent points or not? Okay, so it is not mixed together, but you have to take out some of the sample which is from the analyte itself, okay, from the conical flask. And then internal indicator, so this one will be added together with the solution involved in the titration. So this is like doing your normal acid-base titration, like you add phenolphthalein, you can add methyl orange or methyl red to the test solution itself. Okay, so the method that is preferred would be self-indicators or could be internal, because in external you have to take out just a little bit basically from the test solution itself in order for you to check. Because these two, you don't need to stop the titration. You can just keep on going until it reach the equivalence point or the end point. Okay, some of the example for indicators for redox titration. You can have indigo tetrasulfate, okay, methylene blue, diphenylamine, and their color changes. Okay, so this one color if there is more oxidizing agent or in reduction, so different color. And also here you have ferroin from pale blue to red, so there are different color changes depending on the type of indicators that you use. So some of the terms that you will need to know for redox titration. So endpoint, which is the same, the point at which titration stop, and this is indicated by the color change, okay, of your test solution. And also you have your equivalence point. So this is the point at which oxidant and reductant are in equivalent amounts. So the definition of equivalence point will be different for redox compared to maybe acid and base. In acid and base is neutralization. If you use strong base, strong acid, then the equivalent point will be maybe at pH 7, or the all of the analyte and titrant has been neutralized. But equivalence point in terms of redox, both oxidant and reductant, or the oxidizing and reducing agent, are in equivalent amount. So this actually can be calculated by checking the or calculating the molar mass, okay, and then dividing it with the change in the oxidation number. For example, we have this oxidizing agent of manganese. So for manganate, this one from positive 7 to positive 5, there is a difference in terms of 5, okay, for, in terms of the oxidation number. From positive 7 to positive 2, change 5. So this number 5 will be put over here, and the molar mass is based on the molar mass of potassium permanganate. So the equivalent points will be equal to 158 divided by 5. You're going to get this value, which is 31.6. So this is important so that you know how much of the substance will be needed to dissolve to make the solution, okay, to make the potassium permanganate solution, because later this solution you have to prepare it as a standard solution. So you need to know the exact concentration. So from this 31.6 that you have calculated earlier, which means that if you take this 31.6 and dissolve it maybe in 1 liter of water, so that solution will be considered as 1N. So N is normality. If you want to make it 0.1, so you have to dissolve 3.16 of potassium permanganate in 1 liter of water. So the concentration, if based on this calculation, would be 3.16 gram per liter or 0.1 N. Okay, so 0.1 N. Then for oxalic acid, this one, the carbon itself would lose 2 electrons during the oxidation. So the molar mass for oxalic acid is 90. Okay, 90, while the equivalence point is 90 divided by 2, because it lose 2 electron from the oxalate ion. Okay, oxalic acid, it will come from the oxalate ion. So it means that, so 45 gram, if you dissolve in 1 liter, so you will get 1 N of solution. If you want to make it 0.1 N, then 4.5 dissolve in 1 liter. If you still want to use less number of what do you call that, the solid oxalic acid, you don't want to dissolve this 4.5 in 1 liter, you can also prepare a smaller amount, okay, a smaller volume, but the ratio must be correct. Okay, it must be correct. If this one is divided by 4, 4.5 also must be divided by 4, then only you will get the same concentration. So the concentration would be 4.5 gram per liter, still this one. Even if you prepare it like this, the concentration will be in gram per liter. So it is 4.5 gram per liter, okay, in 1 liter. And the normality is equal to 0.1 N. So example like this, example, it used because the concentration is already given like this, so you don't need to calculate based on this formula. So if the question already give like this, for example, let's calculate equivalence point for the titration of 50 ml of 0.1 m iron 2 plus ion with 0.1 m cerium 4 plus, okay, in a matrix of 1 molar perchloric acid. So the reaction in this case is involving between this iron 2 plus and also cerium 2 plus. So the volume has been given, the concentration has already been given for this iron, but for cerium, only the concentration. So you just have to find out on the volume. So how much of this cerium 4 plus is needed so that it will be in equivalence. So equivalent points meaning both oxidant and reductant should be in equal amount. So you look at the balance equation. So Fe2 plus Ce4 plus, then you will end up with Ce3 plus Fe3 plus. So the moles are the same, meaning that the ratio is 1 to 1. Okay, you have 1 here, 1 on this side as well. So we can say that the moles of iron 2 plus is the same as number of mole for iron 4 plus. Okay, mole will be the same, like 1 mole with 1 mole, but the concentration and the volume could be different. Okay, so what you have to find out is the volume for Ce4 plus or cerium 4 plus. So you just use this M1, basically M1V1 equal to M2V2, but here it's written as MFE, so which is for the iron, times volume for iron equal to the concentration for cerium 4 plus times volume for cerium 4 plus. This is basically derived from number of moles. Moles equals to MV. Okay, so that's why it is written as M1V1 equal to M2V2. So just by putting in all of these values that you have, okay, from the equation, you can obtain the volume for the cerium 4 plus, which is 50 ml. Okay, 50 ml. Now on to the type of redox titration. So there are four main example that I put here. One is the permanganometry using potassium permanganate, and then you have dichrometry from potassium dichromate, and iodometry and iodimetry. So this one involve iodine, and the last one will be serimetry or seric ammonium sulfate. So we are going to look at the first one, which is involving potassium manganate. So this is an example of very strong oxidizing agent or strong oxidant. Okay, it is a very good oxidizing agent, not just in inorganic reaction, but also in organic reaction. Okay, you can convert, for example, an alcohol into aldehyde or carboxylic acid just by using potassium permanganate. Okay, some may use potassium dichromate as well. Dichromate is also a good oxidizing agent, but not as strong as potassium permanganate. So this titration involving potassium manganate is a self indicator, so it doesn't use an external indicator because the color changes from the manganate, which is purple. Okay, purple, very purple color, so you can actually see the difference. So it is not a stable primary standard solution and cannot be obtained in pure form. Okay, because cannot be obtained in pure form, it will have this manganese oxide as impurities. Okay, so not suitable because of these impurities. This manganese oxide will catalyze the reduction of manganate ion, which is this Mn, okay, or what we call as autocatalytic decomposition. So that means even without the addition of the reducing agent, your potassium permanganate might reduce itself. Okay, so this is what we call as the autocatalytic decomposition due to the presence of these manganese oxides. So it needs to be standardized first, okay, before using with a primary standard such as oxalic acid, sodium oxalate, arsenious oxide, or even you can also titrate with ammonium iron sulfate just to standardize first. You can prepare, but then we have to make sure that the solution that you prepare, this potassium permanganate, is exactly having the concentration, okay, as the theoretical value. So how are you going to prepare the potassium permanganate solution? Let's say you want to prepare with this 0.1 N concentration. So just dissolve the solution in distilled water. So basically, this has to be prepared in volumetric flask, okay, in order to obtain accurate reading. And then you can stir the solution, but you can also use the sonicator, okay, ultrasonic bath. So it will shake the glassware that you use, okay, at a very high speed, but ultrasonic level. So all of this solid that you add will dissolve quicker. Then you heat the solution to boiling for 15 to 30 minutes in a water bath, cool the solution, and then you can filter and put it in a clean brown colored glass. Okay, so you place in a brown colored glass to avoid this auto decomposition. And how it is standardized. So you can use oxalic acid. So to prepare the oxalic acid, so normally the oxalic acid is anhydrous, so without the presence of water. So that's why it is suitable to be regarded as the primary standard. So you dissolve 1.125 gram of pure anhydrous oxalic acid, okay, anhydrous, no presence of water, in 250 ml of distilled water. Then you can mix the solution, can use the ultrasonic bath as well. So next step is to pipette out. So this one using pipette, 25 ml into a titration flask. Then you can add 20 ml of dilute sulfuric acid. So a titration flask is uh, the conical flask, okay, that you're going to use. So after that, heat the solution first to 60 or 70 degrees Celsius. So the end point will be when a faint pink color persists for 30 seconds. So once you get this, okay, you titrate. Okay, you titrate with the potassium permanganate. Once you get that faint pink color, you heat the solution until this temperature. So if the color does not change for 30 seconds, if it remains in pink, so that means you have reached your endpoint. So you repeat again in order to get three concordant value. Okay, three readings that can only be differ by what you call that, 0.1 ml. So some of the application with the titration of permanganate, you can use it to estimate the concentration of sodium nitrite. So nitrite are oxidized to nitrates by warm acidic potassium permanganate. So this would be the half equation, and this is the full equation in which you have 2 moles of manganate plus 6 mole of hydrogen ion, and also 5 moles of NO2. Okay, so this will produce 2 moles of manganate and also 5 moles of NO3 minus and also 3 moles of water. So volume and the concentration of the standardized acidified potassium permanganate will be used to determine the amount of sodium nitrite present. So this has to be standardized first, okay, before you can use it to titrate a sample. Okay, you have to standardize. And then dichrometry, also good oxidizing agent as well. It is not as strong as potassium manganate, but one of the advantage is you do not need to you do not need to standardize it. If potassium manganate, you have to standardize it against something first. Okay, like for example the oxalic acid. So you can prepare and use directly. You can use it straight away to titrate. So the color will change from orange to green. Okay, chromate from orange to green. So these redox indicators are used, which will produce this color change. Like for example, you can use N-phenyl antranilic acid, or you can also use phenyl sulfonate in order to add indicators, example indicators. So how the potassium dichromate solution is prepared. Let's say you want to have this concentration, 0.1 N. So find out the equivalent mass. So these values is from the molar mass of potassium dichromate. And then, this one is by having the molar mass divide with the number of difference in terms of the oxidation number. Then you will get these values. So 49 in 1 liter for if you want to prepare 1 N. But if you want to prepare 4.9 or 0.1 N, so you just have to use 4.9 gram. Okay. So how it is prepared? This is by using 1.225 gram of potassium chromate. you need to dissolve in 250 ml of water. So this is having the same concentration as this one. Okay, because you divide 4, 1 liter of water divide 4, you get 250 as well. So this one is not affected by light. So you don't need to store in brown or in amber glass bottle. So you can just place it in normal, the clear color one. Okay, don't need to use amber color. Amber is the brown color glass bottle, like potassium permanganate. So application, the dichromate can be used when you want to determine the concentration of iron 2 plus, so, or ferrous ion. So this is done uh, by using diphenylamine, okay, as indicator, and also the solution requires you to acidify it by having sulfuric acid, okay, sulfuric acid, and also you have to add 3 ml of phosphoric acid as well. So this is how you prepare the test solution, the analyte in the conical flask, before titrating against the potassium permanganate. So this one, okay, you don't need to standardize first like KMNO4. Okay, so the end point is when the orange solution turns green and finally becomes violet blue. So the orange to green is from the color of the chromate. Okay, so difference, because in the transition metal, one of the criteria or special characteristic of transition metal is that they will show different color when in different oxidation state. Okay, so like for example cobalt, cobalt 3 for example will have maybe slightly bluish color, but when it become cobalt 2 the color is purple. Okay, and then you can also have copper 1 will have different colors, but copper 2 will be slightly blue to maybe turquoise color. Okay, so but when it is dissolved, it become an ion. Copper 2 plus will definitely show blue color. Next, the third example of redox titration is iodo and iodimetry. Okay, so don't get confused. You have iodometry and iodimetry. So this one involves the use of iodine solution. So this iodine solution will be used directly for the assay, or an equivalent amount of iodine is liberated indirectly from the reaction mixtures before being assayed. So iodimetry is reducing analyte is titrated directly with iodine. Okay, the analyte, which is the sample test solution, is titrated directly with iodine. So the one in your burette will be your iodine. But for iodometry, so the oxidizing analyte, okay, the one in the test solution, is added to excess iodide ion, okay, in order to produce iodine. Then it will be titrated with standard thiosulfate solution. Okay, so this one is pretty straightforward. So this involves a few steps. So we look into iodometry first. So iodides basically react with another oxidizing agent, but the medium can be either acidic or neutral. Okay, so the iodide, which is from the potassium iodide, Ki, okay, potassium iodide. So this will be oxidized to become iodine. So from I minus 1, okay, to become 0. So the oxidation number from -1 to 0. And the other species, meaning other than the iodide, will be reduced. Will be reduced. Then the iodine, the released iodine, is then titrated with another species. So this titrating species is standard solution in a form of reducing agent. So this is where the reducing iodine will be turned back into iodide. So from I minus to I and then back to I minus. So this one use a standard thiosulfate solution. Okay, so this is involves several steps. So the iodide will be first turned into iodine before being turned back into the iodide solution. Let's say you want to quantify the amount of chlorine dissolved in the mixture. So by using this iodometry, so a known amount of volume of the mixture that contain your chlorine will be put into the titration flask. So you titrate with a known solution of potassium iodide Ki. So the reaction will be Cl2 chlorine plus 2I minus forming 2Cl minus the chloride and also your iodine. So -1, okay, the oxidation number becoming 0, -1 to 0. So this one is oxidized while the chlorine is reduced. So that same mixture that you get just now will be then again titrate. So you do first titration and then you do another titration. That means the first titration, the solution that is in the burette is potassium iodide. The solution that is in the second burette will be the standard thiosulfate solution. So this you titrate with standard thiosulfate solution to determine the release amount of iodine. So this iodine will be turned back into iodide in the second titration. So starch will be added as indicator. So from dark blue, okay, the solution will be colorless. So once you have this, you will have to add starch. So starch will become blue because you have this iodine. So once all of the iodine has been changed into iodide ion, so the dark blue color will become colorless. Okay, will become colorless, as this will signify that all of the iodine has been fully reduced, okay, from 0 to -1. So this can be considered as uh, indirect titration. So it is not straight away. You do your one titration straight away, you can calculate, but you have to do 2 titration in order to get the concentration of your analyte from the first one, which is this one, which is the chlorine, but you have to do 2 different titration. Then for iodimetry, this one is pretty straightforward. So free iodine is titrate with the reducing agent. So iodine reduce to iodide and the other species will be oxidized. Okay, so just one titration only. So the free iodine solution cannot be easily prepared. So iodine is normally mixed with potassium iodide and potassium triiodide solution. So a standard solution of this will be used. Basically, you have to prepare this Ki3 first, okay, in order to conduct iodimetry. So starch can also be used as indicator. So the color change will be from dark blue to colorless as well. Okay, so the general, more like the general reaction will be I2, okay, plus whatever reducing agent that you are using to form 2I. Okay, so this one will be I minus to 0. Then on to the last type of redox titration, which is serimetry. So this one involves using cerium sulfate. So the one in the bracket, like this, if you see cerium in bracket 4, okay, sulfate. So that means that the oxidation number for this metal cerium is 4 plus. So and they will always use Roman numbers. Okay, if you see 1, and then maybe the most common is iron, and then in bracket 2 or maybe 3. So if you see iron in bracket 2, so that will denote that the oxidation number of the iron is 2. If this 3, then the oxidation number will be 3, and when it oxidizes, it will become Fe3+. Okay, so it depends. So if like this, cerium in bracket 4, Roman number 4, so when it when it dissociates it ionize, it will become cerium 4+, like this. So this is also a good oxidizing agent, but it needs to be standardized with dry ferrous ammonium sulfate. So the calculation is done this way. Okay, when you want to prepare the solution, basically the molar mass will be 33.25, but the difference in terms of the oxidation number is just 1, from positive 4 to positive 3. So even though still reducing, but the difference in terms of the number of electrons is just 1. So basically, if you want to prepare 1N solution, you need 33.25 gram of this cerium sulfate, but 0.1 only require 33 grams. So the standardization normally done with the dry ferrous ammonium sulfate. So this has to be prepared first. It requires 3.92 gram, and you need to dissolve in 100 ml of VF, and also add 20 ml of sulfuric acid, H2SO4. Then you need to dilute, take out 10 ml, and then add 10 ml sulfuric acid again, and also indicator. In this case, the ferroin is used. Then only you can titrate with the cerium 4 sulfate. So this is the standardization method. So the endpoint is when it turns red to pale blue. After you standardize, then only you can use the ceric or this cerium sulfate. It can be used, okay, in terms of application by having to estimate the concentration of arsenic trioxide. So this arsenic trioxide solution, you can titrate with the cerium 4 sulfate. So the color changes from red to pale blue. So these two are the half equation for arsenic 3 plus. So this one in bracket, you have the number 3 Roman. So arsenic 3 plus to arsenic 5 plus. So this is oxidation. The oxidation number increase, while the ferric ion just now decreased from 4 to 3. But then you have to times 2 because the number of electrons involved. Here you have 2, this one only 1. So volume and concentration of the standardized cerium 4 sulfate will then be used to determine the amount of arsenic oxide present. Okay, because from here you already know the concentration and also volume of this standard cerium sulfate. The arsenic oxide, you already know the volume, so you just need to calculate the concentration. So in terms of the pharmaceutical application for this redox titration, mainly can be used to do the assay for ascorbic acid or vitamin C, and then assay of paracetamol, PCM. Okay, amount of ferrous ion in ferrous gluconate and also ferrous fumarate. So these two are type of formulation as well, and also in assay of chlorpromazine. Okay, so these are just among the few application in terms of the redox titration. So before that, so that is all on the lecture, but I want to show the videos first.